All right, so part 2 of chapter 4 is types of chemical reactions. So everything we've done up to this point has been reaction and solution stoichiometry. So today we're going to take the reaction and solution stoichiometry that we've talked about, and we're going to start talking about the depths of reaction. So some of this stuff you've seen, but a lot of this is going to be brand new. And the big thing that's in this chapter that always causes everyone issues every year is the dreaded net ionic equations. Okay? Now, we're going to explain it. We're going to talk about it. But it's going to alter your concept of what a balanced chemical equation is. Okay? All right. So, chemical reactions. We know that there are two types of things. There's chemical changes and physical changes. Remember, there are 5 things that must show up to your eyeballs for you to know if a chemical reaction has occurred or not. Otherwise, it's going to be a physical change. Okay? So a chemical reaction transforms elements by compounds into new substances by making and breaking bonds. Circle or highlight that last little sentence right there in red and green. The way we have a chemical reaction is that bonds must be made or broken. Okay? Now, if an intermolecular force is made or broken, is that a chemical change? No, because can water boil? Is it still water? It's the physical change. The balanced chemical equation shows the relative amounts of reactants and products, which basically means you can say grams, you can say volume, you can say molarity, you can say all that stuff. So S, L, G, and AQ, you know what that is. I'm not going to spend time there. And finally, this is a big one, that no energy or time is alluded to. What does alluded to mean? Referred to, mentioned, told, given, any of that. So everything we're going to talk about in this chapter has nothing to do with the amount of energy or the amount of time that it took. When we talk about energy, that is when we're in the electro and thermo chapter, because it's either going to be heat energy or electrical energy or potential energy and all that good stuff. And then when we talk about time, we'll be in the kinetics chapter. So that's where we're going to break everything down to. But it must start with a chemical reaction of some sort. Okay? So there's types of chemical reactions, and there are 7 of them. The great news is that you guys should have seen this. But actually, I'm going to take a pause here, and I'm going to pass something out, and I'll come right. All right, so if you have this part in your packet, it should be this very second page. We'll talk about it later. Okay? We'll talk about it later. So this is what you should have, the very second page. It says that basic types of chemical reactions. So if you did this properly, you should have gone through this summer. And what we're going to be able to do is we're going to be able to utilize this set of notes and instructions, and it's going to tell you everything that we're fixing to cover. So this is going to be kind of your background stuff, so you have this available to you. I'm not going to make copies of this and give it all out. Everything is right there in that packet. So my suggestion to you would be, don't do it now, would to tear these 2 pages out, staple them, and add it to the packet that we're going over. I think it would really help you guys out because it's going to be the specifics of what all of it is, and it gives you more examples of everything and more of a compact, concrete thing. You don't have to flip page after page after page. It's right here in front of you. So that's what I might suggest. And so in all 8 that we're going to talk about, synthesis, decomp, single replacement, double replacement, combustion, acid base, and redox. That's what we're going to cover in this topic. Okay? But it's going to be a new way to look at a few of these that are a little more in depth versus what we're used to. Okay? All right. Now, I do want to ask you this. Are some of these reactions the exact same? It's a trick question. They're not identical, but are they equal but opposite? And that's what I kind of meant by that statement. What is the equal but opposite to synthesis? Decomposition. So if you go and you look at some of these notes, let me back it back out. Let me show it to you one more time. So if you look at the first synthesis reaction, it says a metal plus oxygen makes a what? Metal oxide. We'll scroll down and look. Actually, it should be... Okay. If you scroll down and look at the very back of the second page, number 5, it says some oxides, when heated, decompose into their metal and oxygen. So isn't that just the backwards of everything we just did? Now, if I were actually smart, what I would do is I would go in and I would reorder these in the same order that they're written in up here. So, like, a metal oxide plus water makes a metallic hydroxide. Well, if you come and you look at number 2, most metallic hydroxides decompose into what? Metal oxides plus water. It's the exact same thing except it's backwards. Okay? The exact same thing except it's backwards. All right, so again, I just kind of wanted to show you how you could use that here. Okay? Double replacement are also now known as precipitate reactions. Now, do all double replacement reactions produce precipitates? No, do me a favor. Out beside precipitate or underneath it, please write solubility rules. That is where your solubility rules are really, really, really going to come into play here. Okay? And we're going to talk about those either today or tomorrow, depending on the time that we have. All right, number 4, single replacement. Remember, a single replacement is like you going to the dance and taking someone's date. What was that thing you had to look at? The activity series. Right beside number 4, you do not need the activity series one here. So, you do not need the activity series for single replacement. The reason why is because if you ever see a single replacement reaction on any AP thing, assume that it works. Okay? There will never, ever, ever be an answer, reaction does not work, ever, on anything related to AP, which I think is good news. Combustion, right, must have O2. And then right, mostly hydrocarbons. Must have O2. And then right, mostly hydrocarbons. What is the difference between mostly and all? Okay, so to have a combustion reaction, do you have to have a hydrocarbon? No, okay, because ammonia, NH3, can actually combust. Is there carbon anywhere in ammonia? So there are certain things that we're going to talk about the differences that can actually combust. What's the major thing that you have to have? You gotta have oxygen. Okay. All right. Acid base. You know what that is. Okay. We're not going to go there. My thing about acid base, and you don't have to write this down. Just make sure we're on the same page. For it to be an acid and a base, for it to be an acid-base reaction, do you have to have an acid and a base? Yes. Can it be an acid or a base? You've got to have both of them. Okay? That's not. Now, we'll talk about how that if you see an acid and you don't necessarily know if it's a base or not, we'll talk about how we fight through that later. Okay? All right, and then number 7 is the oxidation reduction, which is also known as redox reaction. We're going to spend a lot of time with that. Remember, in AP, assume all reactions occur. Remember the 5 signs of a chemical reaction: color change, solid, precipitate, bubbles, heat, reaction, light. And then I don't necessarily like the word rust. What word can you put there? Oxidation. So you may want to add that in parentheses behind that. Okay? All right, so synthesis, composition, chemical reaction. So in a synthesis or composition reaction, what's up? Yes, whatever size you want. Yep. Tell her that was a part of the extras. Okay? Composition reaction, 2 or more simple substances combine to form a more complex substance. These reactions from the general form of A plus B makes AB. So my question is, how many reactants must you have? Doesn't matter what they are, as long as you got 2. And how many products would you have? 1. That's what makes a synthesis. One example of synthesis in a reaction is the combination of magnesium and nitrogen to yield magnesium nitride. One of the things that we're going to do when everything gets set up as far as labs is we're going to do the empirical formula of magnesium oxide, and we just kind of show you a basic simple sketch of this. What we're going to have is we're going to have a ring stand, and then it's going to come out here, and then you're going to have a clay pipe triangle, and then we're going to have a crucible sitting on top of it. Okay, it's going to have a lid. Okay, and in here, what we're going to do is we're going to put some magnesium strip. Okay, and underneath it, we're going to Okay, so what we're going to do is we're going to burn it. Okay, and so what's going to happen is you're going to have the magnesium, and what's it going to react with? The oxygen in the air, and we're going to get MgO. Okay, so here's the deal. We're actually going to try to figure out if our empirical formula is correct. Do we get MgO based off of the calculations? Okay, and we'll explain more in depth of how and the way it works. But it does look like a man with a sombrero on. Okay, but it's very simple, but it's very specific, and the calculations are very important to us. Okay. All right, one example of a synthesis reaction. Okay, we're cover that. Another example is combining hydrogen gas with oxygen gas to produce a more complex substance such as water. Right? So if you take H2 plus O2, can you get H2O? Can you? Yeah, you get water out of that. Okay, just like here, you've got magnesium plus nitrogen yields magnesium nitride. As a matter of fact, do me a favor. I cannot believe I've never caught this before, but that picture needs to be deleted. That is not correct right there. That is a single replacement reaction. It's zinc and hydrochloric acid. What's bad news? Okay. All right, so decomposition. So everything that we just talked about, is it possible to break that stuff back down? Yes. Sometimes it's easier to break it down than it is to put it together, and sometimes it's really easy to break it down, or whatever the opposite I said was. Okay. Sometimes it's easier to put together than it is to break it apart, and sometimes it's easier to break it apart and put it together. Okay. That's kind of what I'm asking. Like, it's kind of easy to put Legos together, right? Was it really easy to take them apart? Kaboom! Right? You just slam that sucker down. It shatters everywhere. Okay. And then you can take it from that perspective. Sometimes it's tedious if you have to take it all apart. So it just kind of depends on what's going on. So decomposition is when you take a more complex substance, you break it down. So you've got AB yields A plus B. Bottom line is, how many reactants? One. And at minimum, how many products? Is it possible to have more than 2 products? Say yes. Yes. Okay, so it is possible. One example of decomposition of a reaction is the decomposition of hydrogen peroxide. So if you notice, we've got H2O2. Okay, what's the only difference between hydrogen peroxide and water? There's one more oxygen. It naturally decomposes into water and oxygen. So if I took hydrogen peroxide and poured it to a beaker, and let's say we left it in the sunlight for, let's say a week, and we came back to it, could you pick it up and drink it and possibly be fine? You should be, because what are you going to be drinking? You're going to be drinking water. Okay. So the question then comes up: why do we store hydrogen peroxide in a brown bottle? Okay. Hydrogen peroxide. You're all right. I'm just going to kind of spin it a different way. Hydrogen peroxide is sensitive to UV radiation. It's basically what happens is it decomposes it. There's enough energy in the photons that when it hits the bonds, it actually can separate them. So that's why we put it into a darker color bottle so the light can't penetrate it, so it keeps it for longer. So if you put peroxide in a clear bottle, it will naturally decompose much, much, much quicker. That's exactly why they put alcohol in a darker bottle. Yes, okay, because it will do the exact same thing. All right. Special decomposition reactions. Put a big circle around this page. Okay, this is a part of the notes that I just showed you. You may want to add to this. This is in there, and literally what I did is I copy and pasted it from that sheet of paper. Let me just go ahead and show you. Close right here where it says decomposition reactions. I literally copy and pasted this into your PowerPoint. Okay, so it's the same thing. If you want to go in there and look, I chopped it up a little bit, but it's still the same stuff. But these are the big ones that are going to get you in trouble. Well, let me ask you before I go any further. These are decomp reactions. If we flipped it, would the same thing happen but opposite in synthesis? Okay, so the first one says metallic carbonates break down to yield metal oxides and carbon dioxides. What if I took that magnesium oxide and reacted it with carbon dioxide? What are you going to get? Magnesium carbonate. Does that make sense? So it's the same thing, it's just the opposite. So one synthesis, one is decomposition. We've already done the carbonate, right? Remember the very first question of the first test you guys took was a limestone that was made up of calcium carbonate and magnesium carbonate, and you had to figure out what percentage of that limestone was actually calcium carbonate. Ended up being about 40%. Okay, those are the kind of things that help to know here. Because I've been doing it for 6 years. Same test, yeah. Okay. Now, the next one, metallic chlorates break down into metal chlorides and oxygen. Okay, so if you take lithium chlorate, what are you going to get? Lithium chloride and Do me a favor. Where it says oxygen, what would you write there? Very good. Go ahead and write that in for me. Please, please, please make sure you know that that is O2. Okay? It is a diatomic. Now, real quick, when it says a metallic chloride, will it always be, and please excuse my French here, but would it be always XCl? And what I mean by that, would it be a 1-to-1 ratio? And the reason why is that what happens if you have beryllium chloride? You got to check your charges, right? Okay, you must. What? Just because. Hydrogen peroxide decomposes into water and oxygen. That's one that I would know. Ammonium carbonate decomposes into ammonia, water, and carbon dioxide. We'll see that one a few times. Sulfuric acid and carbonic acid. Do me a favor down there at the very last one. How do you know that one? Carbonic acid decomposes into water and carbon dioxide. Have you ever dealt with that? You ever drinking a flat Coke? That's a flat Coke. Okay, because what makes it sizzle and fizzle? The carbonation. What does the carbonation come from? Carbonic acid. Okay, so when you take that Coke and you unscrew the top and you leave it sitting out on the table for a day, what's happening to that carbonic acid? It's decomposing into water and carbon dioxide. Well, let's think about that. What's happening to the volume of the liquid? Why is it going down? Okay. If you release a bubble out of a liquid, the bubble goes out, and what has to happen to the liquid? It's got to drop. Does that make sense? Now, is it going to be enough of a major difference to be able to tell? No. There's not enough for you to visibly be able to look and tell, but eventually you could. The second thing is, technically, what makes it flat? We know the carbonation is gone, but why? There's more water. So you're diluting the solution. And that's why it doesn't taste as good. Pressure. Sure. That's a good question. I know what you're saying. Basically, how do you get the pressure inside of it if the cap has to screw on top of it? I think it seals it from the bottom. We need to see if there's a how things are made and see if it's how it's made. Yeah. All right. So double replacement reaction. The ions of the two compounds exchange places in an aqueous solution to form two new compounds. Okay. So I've got lead nitrate and potassium iodide, and then what happens to those two things? Change. You need 2 tickets. I don't have change. See if you can find change. Okay. Do you have 2 5s and 2 10? 2 or 5 5s? 4 5s? So again, my question is, what has to happen for this to be a double replacement reaction? Okay. All right. So above this slide, I want you to write this for me, please, or below it, beside it, wherever you can write it. Cats replace cats, and ans replace ans. Okay, so a cation must replace a cation, an anion must replace an anion. One above it, beside it, below it, wherever you can fit it in around the slide, because it's not actually on here. And one of the things that is important is that when I say an anion, can a polyatomic be an anion? Yes. So if you look right here. N led to nitrate. Matter of fact, that's a good point. Can a polyatomic be a cation? There are only 2 of them. Who are they? And mercury 1, right? Ammonium and mercury 1, because they're positive. Yes, it's neutral. Okay, so here's the deal. This nitrate is technically the anion. So notice that over here we just have iodine. But on the product side, notice who potassium is now with. Potassium is now with nitrate. Here's the next thing I'm going to need you to write, and if you can write it wherever you can fit it in, but I would like for it to be right here. check charges. Okay, it's very important that any time you write a brand new compound, you must always check your charges. Now, I'm going to go ahead and throw this out here at this point, and I'm scared to say this, but I think it's important to ask this question. My first question is, over there on the reactant side where it's lead and nitrate, which lead is it? It's lead 2. On the product side, which lead is it? It is 2. I'm just saying this now. Is it possible for lead in a chemical reaction to change its charge? Yes. Chemical change. It is possible. So on the other side, does anyone know the other possible charge of lead is? 4. Iron's 2 and 3. Okay. Lead has a chance that it could show up over there as a 4. Now let me ask you this. Did the oxidation number change? So that should mean that a redox reaction has occurred. Okay? Oil rig, very good. Remember, oxidation is a what? Reduction is a gain. Now let's think about it. It went from a 2 to a 4. Did it go up in value or down in value? This is the trick question. Did that mean it lost electrons or gained electrons? It lost. So lead would have gone through which process? Oxidation. We'll get more into depth than that a little bit later on. But here's the thing. I have never in 6 years seen them write a chemical reaction and then force you to know whether it changes or not. You get to pick what you want it to do. And what would you say is the easiest thing to do? Don't change it. Leave that thing alone. And most of the time it does stay the same. But I need to tell you now, do not freak out on me if you see a transition metal change its charge through the chemical reaction. Because they're called transition for a reason. What does that mean? They can change. They can transition. Okay? Most of the time they stay the same. But don't freak out on me if it does change. Okay? Now, they call this, again, precipitate reactions. Does it always form a precipitate? No. What do you have to check? Your solubility rules. So one of the components formed is usually, I wouldn't even go as far as saying usually, I'd say more rare than not, a precipitate, which is an insoluble solid, and an insoluble gas that bubbles out of solution, or molecular compound, which is usually water. Now, this is the funky one. Let's go back and reread that. So one of the compounds formed is usually A, and it should be a semicolon. There's not a semicolon, but a colon. There are 3 possible things it could be. It could be a solid precipitate, it could be a gaseous precipitate, or it could just be a soluble compound. Okay? If it's a solid precipitate, is it going to collect like a rock and sink to the bottom? What's it going to look like? It's going to be very small, baby tiny particles that are just floating around. Okay? How would you get those particles out? A filter. Okay? If it's a gaseous byproduct, what's it going to do? It's going to turn into a bubble and bubble out of the solution. Does that make sense? Okay? You can't precipitate out of bubble. You can collect the gas, but okay? And then, or it says it's a soluble compound, which you can't see the difference in. Now, to identify the precipitant, you must know the solubility rules. Note that not all double replacement reactions result in a solid or a gas being formed. That's going to be important. Okay? So here's an example of it does performing a solid precipitant. So what we have here is we have, first of all, do me a favor. Based on that chemical reaction up there, okay, see if you guys can write me a balanced chemical equation. Based on those ions in the picture. I'll go ahead and tell you this. I will help you out here. That these 2 go together to begin with, and then these 2 go together to begin with. Yeah. Okay. So you see my 2, you see all 4 species. Write me the 2 reactants and then double replace them. Talk about that. All right, so here's what you should have written. You should, it was chromate, correct? K2CrO4 plus BaNO32 yields KNO3 plus BaCrO4. Okay? And that's not how you should have left it. You should have dropped a 2 on that thing. Now, just out of curiosity, and that you're not wrong, I'm just asking, did anyone write the BaCrO4 first? Is that perfectly fine? As long as it's a product. Okay? This is me, and I'm just saying this out loud just so you understand. What I normally try to do is whatever is first on the left, I try to write it first on the right. It's just kind of a procedure that I always do. Now, here's the questions you guys are at. Go ahead. No, go ahead. Does that make sense? Okay. Now, here's what you guys asked, is how did I know that those two were hooked up to begin with? One of the things that you are going to learn in your solubility rules is all group 1s are soluble. Does that make sense? Hold that thought. Okay. The next thing that you're going to learn is all nitrates are soluble. Okay? Do those two rules affect this reaction? Okay. Let's look at our reactants first. Okay? So, K2CrO4. If I took that solid and I dropped it into water, what's it going to do and why? Why is it going to dissolve? Right here, you alluded to all group 1s are soluble. How do you know that rule applies here? Potassiums are group 1. So what state would we identify as potassium chromate as being in? Aqueous. Would everyone agree with that? Does that make sense why? Okay, let's go to our next one. Barium nitrate. If we drop that solid into water, what would it do and why? Very good. So what state would we recognize that as being? Aqueous. Now here's the fun part. This is what happens when we look at double replacement reactions sometimes, and this is how you're going to know what it is. How you know what ion goes with which solid in the beginning. KNO3. Is that a double whammy? That adheres to both rules. What is going on there? You've got a group 1 and a nitrate. What's the chance of that thing ever being soluble? Insoluble. Never, ever, ever. So what state will we recognize this as? Aqueous. Now, let's go back and let's look at this picture. Look at that picture. What kind of looks gross down there at the bottom? Okay. That is some funky looking yellow stuff. Now my question to you is do you think that beaker is a picture immediately after it was mixed? No. Why can you tell it's not immediately? Because it has settled very good. That's very good observational skills. Because otherwise it would be kind of a cloudy, discolored thing, but it has settled here. So the way we know, based on solubility, is what is the composition of that solid stuff sitting at the bottom? Barium chromate. And I know that today you would not have known that. But if I give you two rules, could you kind of understand it from this perspective? You know a solid showed up, right? What's the only thing it could possibly be? It's got to be barium chromate. Now, the way we know that it has to be barium chromate is, number one, is can a reactant be left over sitting at the bottom? If you have enough of it, but it's not really enough to affect it. It's got to be one of the products. And if you know two rules, this one falls apart, right? Go ahead. Yes. If one of the ions is soluble, the whole thing is soluble. Go ahead. I'm going to hold that thought. Hold that thought. Don't ask me about that because I want to. Go ahead, Madison. No, just nitrate. Yep. Okay, so here's what I want you to do. I want you guys to see if you can figure out. No, I'm gonna help you out with this one. I'm gonna make it easier than harder. So here's your objective. Figure out the products and label the states of matter as they would be. Okay, so here's my first question. Let's do the easy part first. The easy part first is we know this is a double replacement reaction, so we know that who is lead going to hook up with on the other side? Iodine. Now again, I'm just throwing this curveball to you. Is lead a transition? Could it potentially change its charge? Yes, but we're going to assume that what happens? It stays the same. So which lead is it over there? It's lead 2, so it should be PbI2. True or false? True. Okay. And then the other thing is going to be lithium and then nitrate, and they're all one, so that's going to work out well for us. And so we've got lithium nitrate as our other possible reaction. Now, let's go back and let's assign our states of matter. Now, I gave you 2 rules a minute ago. I gave you which rule does our first reaction apply to? All nitrates are soluble, so we're going to assign this an aqueous. Okay, what rule does our second one apply to? Group 1s. Okay. Now, let's go over to our last one, LiNO3. What does it apply to? Both rules. Okay, so it's definitely going to be aqueous, right? Now, here's the deal. You don't know about that other one, right? You don't have a rule for lead. You don't have a rule for iodine. Mason, go ahead. What is it? Very good. Look at you. It's a heavy metal bad guy. Okay, so that is going to be a solid. We'll talk about heavy metal bad guys in a few minutes. Where have you heard that from? Oh, awesome. See? He learned and listened. Okay, we'll talk about heavy metal bad guys. So, Justin, what you were asking me, and this is the reason why I paused you, is because that solution with the yellow color on it, that is lead iodide. Okay, so here's the crazy part. This is reactant A, and what color is that solution in there? Clear. So this could be our lead nitrate, and again, I don't know which one is which. And this could be our Ki. It's probably Ki, to be honest with you, but we'd already done K, and I didn't want to do it again. And those 2 solutions are what color? They're colorless. Okay? Clear's a color. Yeah? It's clear. It's colorless. And you pour those 2 solutions together, and what happens? Boom! A bright, vivid, yellow, solid precipitate forms. Now, when you look at that, the crazy part about it is, does that look kind of liquidy-ish? It looks like it's still liquid, but could you filter that off like with a coffee filter? Yes, and that's how you would know it will be a solid. Okay. Now, my question to you is, if I left it in the test tube, what could I do to dry it out, to dehydrate it, heat it up? Okay, and what that would leave me is a solid component left with just the lead iodide present. Because would you consider it to still be a hydrated form as is? Yes. Okay, you would have to boil it all off. Yes, sir. Yes. Yes. And we'll talk about that, Justin. I don't know. So the formation of a precipitate is a driving force in chemical reaction. A precipitate is an insoluble solid that forms when 2 aqueous solutions are mixed. We often separate the precipitate, PPT, from the solution by filtration. Now, filtration is just a fancy way to say to pour it through a coffee filter. Okay, that's literally what we're doing in what is called gravimetric analysis. Okay? All right, so single replacement reactions. In a single replacement reaction, a single uncombined element replaces another element within a compound. In other words, one element, blah, blah, blah. So it's A plus BC yields AC plus B. And if you put a star beside the purple and gold right there for me, those little sub-bullets on there, I can't express to you how important that is. Now, the one thing about this slide is, do you need the activity series? No, ma'am. No, ma'am. Okay? They always work. Assume that they work in all AP chemistry, guys. Make sure you're awake or alive, one of the two. Okay? All right. So metals replace metals. So if you go to the dance, I'm not going to step off into that thing. One example of single displacement. I need to go ahead and tell you that. If you see displacement and replacement, does that mean the same thing? Yes. To displace something is to move it, or remove it. Replace is to take the place of. Same exact thing. Okay? Is when zinc metal replaces hydrogen and hydrochloric acid to yield zinc chloride and hydrogen gas. Now, real was kind of funny thing is down there at the very bottom it says solid zinc plus 2 HCl yields. There is a big typo in that, and I just called it. Can anyone tell me where the typo is in that last sentence? Nope. Because look, it says where the up arrow is another way to signify gas. Can someone tell me what the typo is? Check the charges. What's wrong with the charges? Very good. It's supposed to be ZnCl2. The reason we know that is because zinc is always a what? 2. So go ahead and do that for me. If you'll drop a 2 on that ZnCl2. And that's why it balances the way it balances. Because if you look at it as it's typed, it's not balanced. There's 2 Cl's on the left and 1 Cl on the right, but I forgot to add the 2 back there. And what I was going to get to before I realized that is what Justin, which you pointed out, is that up arrow is a way to signify that it's a gas. I've never, ever, ever seen that in a real question. I don't know why that's there. I copied and pasted this. A down arrow signifies a solid. Kind of makes sense. Gas goes up, solid goes down. It kind of makes sense. But normally we just use letters. Okay. All right, combustion. A combustion reaction involves a reaction between any combustible material and, circle that red word, an oxidizer. Now, this is a dumb question, but it should make sense. What is the solvent? It's the thing that does the dissolving, right? Okay. So what is the universal solvent? Water. Does everything have to be dissolved by water? No, okay? Oxidizer. What do you think the universal oxidizer is? Amazing. Does it have to be? Keep that in mind, okay? Form an oxidized product. The most famous oxidizer of all is oxygen. Duh, go figure. The unfortunate thing is that until now, most of the examples you've encountered have all involved hydrocarbons. Dun, 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 dun. Not anymore. Okay? So that's the thing that we need you to understand is that not everything we cover in combustion is going to be a hydrocarbon, because the bottom line is it must have an oxidizer and it must produce some sort of oxidized product. Okay? So, why is this unfortunate? Because the desperate search for an algorithm. What is an algorithm? It's a system that always yields the exact same result, right? Okay? So, students often think the only products, and this is my fault, I did this to you, but guess what? Sometimes to get you to understand it, I have to lie to you to get you to the truth. Okay? You think the only products of combustion are the oxides of carbon, which is carbon monoxide or carbon dioxide, and the oxygen of hydrogen, which is water. Think about that for just a second. If we have a hydrocarbon, do you agree that that is CXHY plus O2? It says that your products must be oxidized versions. Would you agree with that? Well, that makes a whole lot of sense. Because the oxidized version of carbon is carbon dioxide, an oxidized version of hydrogen is water. Does that now kind of make logical sense? Yes, no, maybe. You've never thought about it from that perspective, but that's the actual reality of it. Pretty much. Boom. It goes real big boom, boom. Sir. We'll talk about that. We're going to get there. Okay. So, and thus, silly things on the AP exam shown below. An example, write a balanced chemical equation for the burning of magnesium ribbon in air. Mg plus O yields CO2 plus H2O. What in the HE double hockey sticks is wrong with that? There's no carbon nor hydrogen in the reactant, so what you start with, you must end with. That should be common sense. Why, logically, do you think that they said, oh, that's combustion, boom, and other products? They saw something with oxygen. Okay? Burning. Burning means boom. People assume that, so they say, oh, that's a combustion problem. The products are always that. But now we know that if you take magnesium and you burn it in oxygen, it's going to yield magnesium oxide. Is that an oxide version of the reactant? That's combustion. Okay? So you've been lied to slightly. I wouldn't necessarily say lied to. You haven't been told the full truth. Okay? Because here, I didn't lie. I never told you anything wrong. I just didn't tell you the whole truth. I didn't tell you the full extent to of how it goes. Okay? So, additionally, most folks think of combustion in the literal burning sense. But here's the cool part. Cellular respiration involves one of the most famous combustion reactions of all time. But are we constantly on fire? Technically, we are kind of warm people, right? 98.6 degrees Fahrenheit, that's kind of warm. Okay? And there's a reason why our body heats up. When you get nervous or you get scared, you start sweating, right? Your fight or flight syndrome kicks in because you're burning a lot of energy. And when you burn that glucose, that energy's got to go somewhere. Okay? And so this is what's going on. Our body is constantly going through cellular respiration. It's going through metabolism. All of those things are considered somewhat of a combustion reaction because if you look at it, what is C6H12O6? Glucose. We're mixing with oxygen. We're getting our carbon oxide product, and we're getting our hydrogen oxide product. And in cellular respiration, what form of energy are we getting? Come on, AP Bio people. Come on, Chance, Ryan. What is the form of energy we get from cellular respiration? Thank you, ATP. A B, and you don't know what ATP is. You need to be kicked in the teeth for that. Sorry, that was violent. I apologize. Okay. All right. Dude, you got to quit, man. Now, this is going into a little bit of a biological sense because I think it's important that you guys understand the biology of it. The main difference for cellular respiration is that energy released from glucose is performed in a very controlled manner, which means that your body sustains this energy for long periods of time, right? If I asked you to go run a mile, and none of you would, okay? Some of you might because you're weird, but the deal is that if once you got finished with your first lap, if your body burned through all of the energy that it had stored up, would you be able to continue? So your body naturally knows how to selectively and control its energy consumption. An algorithm. Okay? It's designed that way. Now, does your metabolism have something to do with it? Yes. Does the types of food you eat have something to do with it? Yes. Does your experience with exercise have something to do with it? Absolutely. Jamil, you're on the track team. If we went out there and ran, you would beat me far long in advance because you're trained in that. I could barely run to the office from here. Okay? I'm just saying. So those are the things that you have to kind of deal with. So the enzymes, this is important. This is the biology, but we're going to get into this. The enzymes, control manner and using enzymes to both lower the activation energy. This is something that some of you have seen before and has been a really long time. This was a type of reaction graph. What type? This is exo. The reason why it is exo is because this is the amount of energy and this is time. So, do you end with more or less than you began with? You end with less. So think about it from this perspective. What is the slope of that line? Negative. So are you giving energy off or are you putting energy in? You're giving energy off. So this is an exothermic type of graph. So what is the activation energy? If I asked you to kick this ball over that hill, does it require a certain amount of energy? Yes. And that's what the activation energy hill is, E sub A. So what enzymes do in your body is they're there to shrink that hill. Okay? They make the reaction happen either harder or easier depending upon when you need that burst of energy. But in a chemical reaction, we don't have enzymes. What do we have? You said it. Yes. That's what a catalyst does. Catalysts are chemical versions of biological enzymes that we can do to put into a specific reaction. Real quick, I'm almost done. I want to finish this slide. Okay? So what we can do is we can spread out the energy release into small steps over a relatively long period of time. For combustion, the initial activation energy is high. A high temperature needed to start the burning. So if I took a hydrogen gas and I wanted to light it, what do I need to make it go boom? I need a match. I obviously need oxygen. But to overcome that initial energy, because are all hydrogen gas molecules able to be ignited? Well, when you take a match and you put it in there, they begin to ignite, right? So that's kind of what's going on here. But as seen at high pressure, high temperature needed to sugar burns while cooking. And the energy release is very rapid, with all of the chemical energy stored in the bonds released near instantaneously, providing very large amounts of energy in a short period of time. It basically comes down to a controlled form of burning. You guys have seen the whoosh bottle, right? Okay. You put the thing in it, you put the lighter, and it looks like a jet engine taking off. I've showed you that. Okay. So that is a form of combustion. If I have some alcohol, yeah. Exactly. Okay, so it's releasing energy.